the closing course in some sense. Okay? So this morning I will just sort of follow up on my lecture of yesterday. Is just a binary alloy. So why is a binary alloy simple? Well, in a binary alloy you have two components, but if you make the assumption, as I will again do, that the molar volume is constant, then as you have seen yesterday, you can eliminate one of the concentrations and you have one variable to treat, which is the composition, that is the fraction of B atoms, say. So I will, like yesterday, I will say we have a constant molar volume and the transport of this solid is exclusively by diffusion. So we have a single variable. And just like for the Cahn-Hilliard model, of course, we can use our general description from out of equilibrium thermodynamics. The solute currents are given by the negative gradient of the chemical potential times the atomic mobility. And the composition obeys a conservation law, so the time derivative of the concentration is the divergence of the current. So all of this is exactly like in the Cahn-Hilliard equation. Now, people, of course, have been interested in alloy solidification for a long time. So the first models for alloy solidification were written down in the beginning of the 90s. And if you follow just the standard recipe that we have learned so far this week, that's what they did. What would you write down? Well, just like yesterday for the pure substance case, you would write down, well, the phase field is an order parameter, so I write down an Allen-Kahn equation. And the concentration is a conserved quantity. So this looks just like Cahn-Hilliard, so I write the same equation as for the free energy. You have to write down. I have written it here in this form, which was like what I wrote down yesterday. There is the interface part, which is the double well in the phase field, plus the gradient squared in the phase field, so always the same. And then here is the thermodynamic part, so TD means thermodynamic. And this is just, I did like this yesterday, it's the solid free energy now as a function of temperature and composition, multiplied by this interpolation function here, which is 1 in the solid and 0 in the liquid. And here's the liquid free energy multiplied by 1 minus G, which is 1 in the liquid and 0 in the solid. So as I've said yesterday, this is just an approximation of the two-phase bulk free energy. So this is the solid free energy in the solid domain plus the liquid free energy in the liquid domain, right? So that was the first model that was written down, but there is a problem with this. What's the problem? The problem is actually that there is a non-zero thermodynamic driving force for the interfaces. What do I mean by that? Well, see if I write down the phase field equation using my standard recipe. So I do dt phi is minus big gamma times the variational derivative. What will I get? I will get formally the same expression as yesterday for the pure substance model. I will get the Laplacian. Oops, this should be a k, not a sigma. Here is h times the derivative of the double well potential. And here I get the derivative of the thermodynamic part, which looks like this. There's the derivative of this interpolation polynomial. And here I will get fs minus fl. So this is exactly the same as for the pure substance model, except that now the free energies depend on T and C and not only on T. Okay? But this is a decisive difference. Why is that? Because we have seen yesterday, I've done these calculations on the blackboard, that for a pure substance, if the free energy only depends on T, at the melting point, solid and liquid free energies are the same. Whereas for a binary mixture, we have gone through that yesterday. Their equilibrium is given by the common tangent construction, and the common tangent construction is equivalent to these two formulas, that is equal chemical potentials in the two phases and equal, in quotes, grand potential in the two phases. And of course, if you look at this graph, the two points where the double tangent touches is here, and of course, you see that the free energies of the two phases are not the same. Which means if you go back to this equation, in this term here, well, this factor here will not be 0, even at equilibrium. Okay? Which means that if you look at the equilibrium equation for the interface, which would correspond to dt phi equal to 0, you have these two terms, which are the traditional terms. These are the terms that give the hyperbolic tangent solution. But now you have added a new term here, which is non-zero, which means that the tangent hyperbolic solution is not valid anymore. The solution will be something else. It will again look like an interface shape, but you will mix in that solution the properties that you assign to the interface and the properties that come from the bulk thermodynamics, which makes things complicated. Okay? So that's the problem with this model. You inherently mix bulk and interface properties. You cannot cleanly separate them. So to state this in a little bit more precise manner and to picture what should be a way out, let's look a little bit at this equilibrium interface solution. So as I have said, the common tangent construction that gives you the phase diagram fixes you the slope of this red line. So the equilibrium value of the chemical potential is given. Okay? Now the difference between a thermodynamics calculation and a phase field calculation is actually that this equation must be valid not only for the bulk compositions, but it must be valid through the entire interface. Okay? And this is what is expressed by this equation. So I calculate the variational derivative of with respect to the composition, which is equal to the chemical potential, and this must be equal to the equilibrium chemical potential for the whole interface. Now if you just do the calculation of this interpolated free energy, of course you find interpolation function times dfs by dc and 1 minus g times dfl by dc. Now for a fixed temperature, of course this is a function of c and this is a function of c. So what this equation actually represents is a relation between mu and c. And since mu is fixed, this is an equation for c as a function of the phase field phi. Okay? This is the constant. The phase field phi varies through the interpolation functions, and the composition c varies because of the free energy expression. So this is an implicit equation for c as a function of phi. Okay? I cannot necessarily invert this, but I can always write down that the consequence of this condition here, constant chemical potential, is that the equilibrium profile is a function of phi. Okay? Now that means if I calculate the variational derivative of this thermodynamic free energy with respect to phi, for the equilibrium profile, I have to do it in the following way. I take first the partial derivative of this whole function with respect to phi, but then this function also depends on c, but c for the equilibrium profile is also a function of phi. So I have to take into account that I have to take the derivative with respect to c, and then I have to take the derivative of this function with respect to phi. Simple chain rule. So the total derivative of this thermodynamic part with respect to the phase field is this. And actually what you get when you combine this, if you look a little bit, you can see what this is. This is the chemical potential, which is equal to the equilibrium value. Okay, this is the derivative of c with respect to phi. This is the derivative of f with respect to phi. So you see that this is the total derivative with respect to phi of f minus mu c. Okay? And at the equilibrium, this should be 0. So now you can exactly grasp the sense of this condition here. Equilibrium thermodynamics just fixes you the position of these 2 points. So it tells you this function is the same in the 2 equilibrium phases. If you want a well-behaved phase field model, you need a stronger condition. You need that the profile through the interface actually goes exactly along the red line, because through the whole interface, f minus mu c should be a constant. Because if this is the case, then the last term is 0, and then I'm back to my simple interface equation that I like. Okay? So the construction of a good alloy phase field model has to ensure that the interfaces are such that this function is a constant. Okay? Now, this was identified quite early on, and there have been proposed various ways to achieve this. So, first of all, you can try to construct such models for special cases. Okay? And I was involved in a work which did that. If you have the specific case of a dilute alloy, you know the free energy functions, which have a specific functional form. And what you can do is you can modify the interpolation with respect to the phase field in such a way that this condition is satisfied, and that way you get out a well-behaved model. So that's what we did for the dilute alloy model, which for quite some time was the only model available that had that principle. And then there is a very general approach, which is often referred to as the Kim-Suzuki model, okay? But the main idea was also already contained in this paper written by the group of Access in Germany. So what is the idea? For me, it looked very strange in the beginning, but it actually works. So these are well-behaved phase field model for solidification. What these persons suggested was, okay, the problem comes from the fact that in the interface you assume a concentration profile, and you assume that in both phases you have the same concentration. Let's switch the picture to a different viewpoint, and let's think of the interface as a superposition of two different phases. And let's assign each phase a separate concentration. So the subtle difference is now their interpolation is the free energy density is the solid free energy taken at concentration CS, and the liquid free energy taken at the concentration CL, which may be different from CS. So you have one more degree of freedom because now you have two concentration variables. Okay? And of course, then you have to ask yourself, well, two concentration doesn't make sense if I'm on the same space point. So you have to give a prescription how to calculate the true concentration. And they said, well, the true concentration in this picture of superposition between two phases should also be an interpolation between the phase compositions. Okay? But still, you have added 1 degree of freedom to the problem, so which is physically not there. So you have to also give a prescription how to relate the solid and the liquid concentrations. And so in the first paper by the Access group, they did this using a simple partition relation that is saying that the solid concentration is the partition coefficient K times the liquid concentration. Kim-Suzuki generalized this because they said, okay, actually this condition should be given by the condition that the chemical potential in the two phases should be the same, because in an interface you can have rapid exchange of particles between the two phases, and as we have seen, if you have an exchange between two systems, the chemical potential should be the same. And you can easily show that this is a particular case of this for dilute alloys. Okay, so the partition relation comes from the fact that the chemical potential is the same in the two phases. If you work this out with the free energy of a dilute model, you will get this. So this is this is the principle, and it's still applied by many people and in many models. Why I didn't like this? It's first, I'm sort of reluctant to accept the idea of separate concentrations. It's contrary to my intuition. If you think about coarse graining, there should be a simple concentration variable. And also, you know, if you want to solve this model, actually, at each interface point, you have to solve this equation. And if you think, for example, about the Kalfat representation of free energies, it's not trivial. You need to do some kind of Newton solver or whatever to obtain the solution of this equation at each time step. So it's numerically costly. So then in 2011, actually, both myself and Abik had about the same idea. The idea is, okay, well, maybe one can write down a different model where you don't start from the free energy, but you start from this grand potential that is this function F minus mu c. And so you should redo the thermodynamics in this new perspective. Okay? So I will rapidly go through this with you, but I think I have formulated the idea already many times. This is to exploit the perfect analogy that exists between a pure substance, where the transported quantity is heat, and a binary alloy at fixed temperature, where the transported quantity is solid. Because if you go through this thermodynamic, you can see that there is an analogy between many quantities. So the transported quantity is heat in the case of pure substance and solute in the case of binary alloy. Well, so this is an extensive quantity. You have currents of this quantity. The intensive quantity that drives the current of this quantity in the case of pure substance is temperature. In the case of alloy, it's chemical potential. If you write down a thermodynamic potential in the extensive variable, for the pure substance it would be the entropy, and for the alloy it would be the free energy. If you write down the thermodynamic potential in the corresponding intensive variable, for the pure substance it would be free energy, and for the mixture it would be the grand potential. And now you see, in some sense, in a nutshell, where the problem comes from. For the pure substance, we had formulated everything in the free energy, which is the thermodynamic potential that is written in the intensive variable. Whereas if you use the free energy for the alloy, this corresponds to the thermodynamic potential for the extensive variable. So things are not the same. Whereas if you use this one, which is the equivalent of the free energy, everything should be the same. And as you will see in a few steps, indeed everything is the same. So here is the differential of F, which I have written down many times. So the chemical potential is the derivative of F with respect to N. If you do the Legendre transform, you go from F to omega by writing omega as F minus mu N. Omega actually becomes a function not of the composition or the number of particles, but of mu. And this time, the average number of particles is obtained by the derivative of omega with respect to mu. So you see again conjugate variable here. Mu is df by dn here. N is minus d omega by nu mu. Same thing as for pressure and volume or energy and entropy. So here two remarks of caution, which are the same that I already have made yesterday. In principle, for a binary alloy, you should have two chemical potentials. But if the molar volume is constant, then the number of particles is conserved. You have DNA is minus DNB. And so there is only one non-trivial chemical potential, which is often called the diffusion potential. So just the same as in the Cahn-Hilliard equation. And also, again, the same point. If you take nu equal df by dc, this has dimension of energy per unit volume. So in the following, instead of working with c, I will often work with rho, which is the number density, so which is the composition divided by the atomic volume. So what's the atomic volume? The atomic volume is simply the molar volume divided by the Avogadro number. So it's the volume occupied by one atom. Okay. But, I mean, don't get confused. If I write rho, you can think C. It's just a matter of changing the dimension of this quantity. Okay? So, if I introduce this rho, actually the grand potential density is F minus mu rho. So now mu is an energy, and rho is number of particles per unit volume. And I can always define this function if my free energy f of c is a convex function. Okay? This is just a property of the Legendre transform. If your function is convex, then the Legendre transform is simple and unique. Okay? So what I will do now is just to go through the same steps as for the pure substance yesterday. So I write the total grand potential as the sum of the interfacial part and the thermodynamic part. The interfacial part will be the same as always. double well plus gradient squared. And the thermodynamic part now will be exactly the same as before, but now I interpolate not the free energies, but the grand potentials. Okay? So again, this is the solid grand potential, so the grand potential in the solid domain, plus the liquid grand potential in the liquid domain. So my interface equation now becomes this, and you see that now there is no problem because these two quantities are the same in equilibrium. Right? That we have had several times. The condition for equilibrium is that these two quantities are the same. So this term is not there, and I get the right interface equation which just involves K and H. So I can do this whole game of changing the interface thickness by changing the coefficients K and H. I don't need to worry anymore about the thermodynamic part. Okay? Then we need equations of motion. So the equation of the phase field is the same as always. You just take the variational derivative and you write down the Allen-Kahn equation. So the question is, what's the equation of motion for mu? Because as I have switched from the free energy to the grand potential, I've switched variables from C to mu. So now I need an equation of motion for mu. But for this, I can exactly follow the same steps as for the temperature yesterday. So first, I take the variational derivative of omega with respect to mu, which will give me the negative of the concentration. And this concentration will actually be an interpolation of the solid concentration and the liquid concentration. Just like yesterday, I interpolated the entropy between solid and liquid, and the entropy was the derivative of the free energy with respect to temperature. So you see, again, the perfect analogy between omega and F and mu and T. Right? So rho here plays the same role as yesterday, the entropy density. And then this rho, so defined, is a function of phi and mu. So if I calculate the variation of rho, I have the part that depends on phi. This will describe me the concentration difference between phases. So if I change the phase, then the concentration varies. And here, this is the variation with respect to mu. This will give me the diffusion part in some sense. So if I calculate this here, d rho by d phi, precisely, I will see the concentration difference appear with here the derivative of the interpolation polynomial. And here I define a quantity which I call chi. And chi is just d rho by d mu, which can be related to the second derivative of the free energy. So this second derivative of the free energy is often called the thermodynamic factor. So this chi is just the inverse of the thermodynamic factor. So this is something that depends only on the free energy curves. So if I give you free energy curves, chi is given. Okay? So then, just like yesterday, if I divide this by dt, I get an expression for d rho by dt, which will be proportional to d phi by dt and d mu by dt. So I invert this to get d mu by dt, which is here. And then here I get d rho by dt. And d rho by dt I can replace with the conservation law here that we had before, because dt rho is the divergence of the current. So here on this side I will get the divergence of m grad mu. And now I can use precisely that the mobility can be written as the product of this inverse of the thermodynamic factor and the diffusion coefficient. Actually, we have seen this yesterday as a calculation on the blackboard. I have told you that minus m grad mu could be written as minus m times d mu by dc grad c by using the chain rule, and you see that this is equal to the diffusion coefficient. So indeed you can see that m is equal to d divided by d mu by dc. Okay? Which is precisely what is written here. Okay? Because chi is 1 by f prime prime. So it's just the multiplicative factor that appears here. So if I put these two equations together, what do I get? I do an equation for dt mu. Here, from where is it? From here, I have the multiplicative factor d chi chi here, so I get a 1 by chi outside, and this chi here appears through the diffusion term, and this term here comes from the phase change, which contains the concentration difference. Now, what's one important difference with respect to the pure substance equation is usually this susceptibility, this function chi. This is in some sense the equivalent of the specific heat in the pure substance case. Specific heat is the second derivative of the free energy. Now, the specific heat often you can assume to be constant, but this function often is a very strongly varying function of C. So you cannot assume that chi is constant, which means that you cannot simplify it here, because upstairs it's inside the divergence, and downstairs it's just a prefactor. So unfortunately, I cannot simplify this equation. I just have to leave it like this. But so this is the equation that you have to solve. Okay? And if you want to solve it for a concrete case, you have first to specify the free energy function. If you have specified the free energy function, from this you can calculate the chi, and you can calculate all the other things, and then you can solve the equation. And you will see an example how to do that just next in the tutorial. Okay? Now, there is one problem. So this is an equation that works perfectly well for arbitrary free energy. So you can take a Kalfat energy, free energy, and you can go through everything. Generally, you cannot do that analytically, but well, that's why we have computers. So the equation is set up, the recipe is there, and it works, right? But there is one other problem left that I will briefly tell you, even though probably you're not going to program this, but it has been an important progress, and it also illustrates, once again, the difference between this top-down and bottom-up approach, right? Because there is one other very important difference between the alloy solidification case and the pure substance solidification case. So remember, the pure substance solidification was driven by the transport of heat, and heat diffusion is about of the same magnitude in the solid and the liquid, meaning the heat diffusion coefficient in solid and liquid are often of a comparable order of magnitude. So remember, yesterday I have made the approximation that the diffusion coefficient is a constant, right? This makes the mathematics particularly simple. For alloy solidification, this is a very bad approximation, because normally chemical diffusion is much, much slower in the solid than in the liquid. And so in alloy solidification, mostly people make the opposite approximation. That is, they say there is no diffusion in the solid. So instead of the symmetric model, they take this model where the diffusion is 0 in the solid, and this is called the one-sided model, because diffusion takes place only on one side of the interface, on the liquid side. Now actually this creates a problem. And to illustrate this problem, remember yesterday I have shown you this plot that illustrated how this asymptotic matching procedure is working, which showed you the profile of a diffusion field, which is the black line, when you go through a phase field interface. Okay? Now yesterday, the little u was a dimensionless temperature. Here you can think of the little u as a non-dimensionalized chemical potential. Okay? So what I'm plotting is the solution of this equation when I couple it to the phase field equation. Okay? So a one-dimensional solution of an interface that moves forward. And just as yesterday, you see, well, here I have a gradient in chemical potential, so this drives a solute current. So the solute is evacuated here, and this makes the interface go forward. And inside the interface, this term here will redistribute the solid. So I will have a source term for the chemical potential that is proportional to the difference in the concentration between the two phases. Just like in the thermal case here, I had a source term that was proportional to the latent heat. which is the difference in internal energy between the two phases. Once again, perfect analogy. Okay? So if you remember yesterday's graph, the profile looks fairly similar. But if I repeat now the same procedure as yesterday, that is, I fit an asymptote here and I fit an asymptote here, what do I get? Here's the picture. So you see the two ends do not have the same intersection point with the interface. Okay? Which means that, remember, these intersection points were the boundary conditions that the outer field sees. That is, even though the microscopic field mu is perfectly continuous, on the outer scale it looks like as if there is a jump in chemical potential at the interface. Okay, so the interface, the chemical potential on the macroscopic scale is discontinuous at the interface. Now, how can this happen? Is this real? Well, the answer is unfortunately yes. It is real. It corresponds to a real physical effect. It's the physical effect that is known as solute trapping. So what's solute trapping? Well, you imagine if you solidify a binary alloy, well, here I'm treating the isothermal situation, but just think a normal metallurgical process. Usually solidification occurs by the extraction of heat. But the extraction of heat can be very quick because heat diffusion is fast, whereas chemical diffusion is slow. So you can have that the speed of a crystallization front is set by the extraction of heat. And then the solute has sort of to manage to get out of the solidifying crystal, right? So if you think about the dilute case, in a dilute solution, usually the solute has less, the crystal has less solute than the liquid. So when the liquid crystallizes, this supplementary solute has to get out of the crystal. And of course, it has to get out by diffusion. But in this case, when you have a rapid heat extraction, the velocity of the interface is not limited by the speed of solute diffusion. It's limited by the speed of heat diffusion. So the interface can go, in some sense, much faster than the solute can cope with, in some sense. Okay? And now to see what happens is, actually, you have to compare two characteristic times. One is the time that the solute needs to get out of the crystal. Okay? And if you stick to the thin interface picture, solute has to get through the interface by diffusion. What's the characteristic time for that? Well, you can construct a time scale by taking W squared, which is the interface thickness, and divide it by the diffusion, the solute diffusion coefficient. Okay? W is meters. The solute diffusion coefficient is meters squared by time. So this is the time. It's the time, characteristic time that you need to diffuse through the interface. So in some sense, this is the time that you need to equilibrate both sides of the interface, because you equilibrate both sides of the interface by exchange of solute atoms, and this happens with diffusion. And then there is a second time scale, which is the time that the interface needs to go forward by once its thickness. And this is a simple geometric time scale. This is just W by V. W, again, the interface thickness, and V is the interface speed. Okay? Now you can see that if this advancing time is much smaller than the equilibration time, then the interface will not have the time to relax to local equilibrium. That is this exchange process of solute atoms, which would lead, as we have seen yesterday, to an equilibration of the chemical potentials, does not have enough time to take place. Okay? And the characteristic parameter that describes you how far you are from the from equilibrium, you can get by the ratio of these two time scales. Now, which one are we going to take upstairs? Yeah, well, so we can form a parameter which is the relaxation time divided by the advance time. So this is W squared by D divided by W over V. So in the end I will get W V by D, which you see is the ratio of the interface thickness and the diffusion length. And just to give you an order of magnitude, well, see, if I take an interface width of 1 nanometer, and if I take a diffusion coefficient of 10 to the minus 9 meters squared per second, then you see that in order to have these relaxation times the same, it's sufficient to have a velocity of 1 meter per second. Now in reality, these characteristic velocity scales are a little bit smaller, because here I have taken the diffusivity in the liquid. Now in the interface, the diffusivity is rather lower than in the liquid. So say if I take a 100 times lower diffusivity in the interface than in the liquid, then I get 0.1 meters per second, or 1 centimeter per second, right? And centimeter per second is fast, but it's perfectly reachable in rapid solidification processes. Okay? So, if I say the equilibration of the two sides of the interface doesn't take place, that means there is a chemical potential jump between the two sides of the interface in real systems if I go fast enough. So this has been well documented, has been measured in experiments. There have been models for this which contain this small parameter. So it's a physical effect. Now what's the problem for us who want to model solidification microstructures? Well, you have seen yesterday that in order to do that, I would like to use interface thicknesses that are much larger than in reality. Now say if I blow up the interface thickness by a factor of 100, then of course solute trapping sets in at velocities that were 100 times too small. So if I was at 1 centimeter per second, if I divide this by 100, I get 100 microns per second, which becomes dangerous because that's typical velocities that you would like to simulate if you talk about metallurgy, right? So the problem is that if you blow up the interfaces, it will appear for conditions where normally it's not there. And that's because in this physics for the first time, we explicitly have the interface thickness that appears in a relevant parameter. Okay? So for this process of solute trapping, the interface thickness is a relevant parameter. So for a long time, people were stuck there. They were doing phase field simulation, but the results were not accurate because solute trapping was in there. Okay? And then for the moment, the only idea that has come up to correct this problem is to sort of do an add-on. And I always say, okay, well, solute cannot get out fast enough. Let's take a shovel and shovel it out. Okay. So the idea was to introduce what was called an anti-trapping current. So this is this thing here. So it's an additional current that you put. Here is the solute current. This is the standard thermodynamic solute current. And you add another one. And this you make proportional to the interface thickness and to the interface velocity. The interface velocity is proportional to dt phi and to a certain interpolation function a of phi, which you have to fix doing matched asymptotic expansions. Okay? And if you want all the gory details how to do that, you can find this here, where there is like 10 pages of asymptotic calculations. You have to be motivated to go through, but I think all the details are there. Okay? Now, in some sense, we were hesitating for quite some time to do this because in reality it's quite horrible. Because this thing you absolutely cannot derive from thermodynamics, right? It's just, you plug it there, you motivate it by these much asymptotic expansions, but you cannot motivate it by thermodynamics. So in all this phase field, like I have explained it to you, this is really a very new element, because up to now, I've derived everything from thermodynamics. So this is the first time that we have an element that is necessary for quantitative simulations, but does not come from thermodynamics. So to come back to my usual language, this is a thing that you cannot get by the bottom-up procedure, that you can get only by the top-down procedure, because you say, I want to simulate a certain problem. If you do the bottom-up thing, you get an undesirable physical effect that you do not want to have. So you have to throw it out by hand. Okay? In order to use phase field models as a quantitative tool for simulations. Okay? So this was a quite revolutionary proposition which was attacked, and but now it's used in many different models. And recently there have been some efforts or some attempts to justify it thermodynamically. I don't really fully believe in those, but there are still people thinking about these things and how you can maybe get this from a bottom-up approach. So if you have a new idea, you're very welcome to try, because this is a sort, in some sense, it's a heresy, right, in the whole approach. Okay, but with this it works, and the demonstration is always the same. So I put up the next graph right away. So here what I have done, this is one graph of my 2011 paper. I have taken the nickel-copper phase diagram. So this is a standard lens shape phase diagram. So you can do a regular solution model, or even an ideal solution model for that. And I have gone to exactly c equal 0.5, and I have placed myself right in the middle of the coexistence zone. So this is a well-defined physical system. I have fixed an anisotropy value, and I have calculated dendrites. And here you see, I don't even have a picture of the dendrites, but that's not important. What is important is the dendrite tip growth speed as a function of the interface thickness. And as you can see, it converges quite well. So here you see, if you draw by line, in your mind a fit through this point, you see that the real growth speed that you would approach with zero interface thickness would be like 140 microns per second. And you see, if I have an interface width of 200 nanometers, that is 200 times larger than the real value, I'm still at 150, so just a few percent off. But I have gained 200 to the power 5 in calculation speed in a three-dimensional simulation. Now this simulation is two-dimensional. Actually, you also see another thing. If you stare at this long enough, if you interpolate these values, what type of curve do you see? Parabola. Yes, I've seen you say this. Yes, it looks like a parabola. And this is just a remark. Actually, this is very nice. It should be a parabola. And why should it be a parabola? I have talked to you about this much asymptotic expansions procedure. Okay. I didn't give you the detail, but much asymptotic expansions. Expansion means a power series expansion. So you expand the powers of this interface thickness, and then you equate order by order. So what often is called a quantitative phase field model is a model where you have eliminated all the linear errors. Okay. Then logically what you should see first as an error is the quadratic one. So I would generically expect, if you do such convergence curves, that you should see a quadratic dependence. So in the plot from the original Kramer-Rappel paper that I showed you, this was not the case. But this was because at the time computers were very small, so they had to push discretization and all other parameters to the very limit to be able to do that. So there is a mixture of various errors. There's computational errors, discretization errors, and the error in the expansion. Nowadays, computers are much more powerful, so you can choose a discretization that is fine enough to see this second order error of the asymptotic expansion. So everything works fine. Here is a plot, I think, from our 2004 paper. What you see here is a solidification cell, so it's a solid finger that grows upward in a temperature gradient. And same thing, here what varies is the interface thickness, because D0 is the capillary length, so it's a fixed parameter. And you see the blue dots are the thickest interface, and the black line is the thinnest. And you see that for the last two values, the interface shapes almost exactly superimpose, which means that, again, this model converges well. So you can get results that are independent of the interface thickness that you choose. Okay? So then you can have fun with this, and I just put up one little movie. So here I simulate directional solidification. So this is a planar front. It grows upward, and there's a temperature gradient. Of course, you will see solidification cells developing. So, up. So this grows upward, and with my virtual camera, I follow the front. So you see that you can study phenomena of considerable complexity. So there are solid cells, you have grooves in between, and then in between three cells, you have a liquid channel that forms. You have pinch-off events and all that. And so this can quantitatively describe solidification cells. Now here, my simulation box, actually, for this three-dimensional simulation, the cross-section was 240 by 240 grid points. Typically, one solidification cell is 100 microns in diameter. So with a reasonable computational effort, you can simulate here a system that is almost 1 millimeter squared in section. So this starts to be a scale where you can do really interesting things for metallurgy. Okay? So this is the end on the part on the alloy phase field models. Now I will just do a very small add-on, because yesterday I skipped the part, an important part that you will need this afternoon, because we always talk about dendrites, and as I have mentioned, dendrites you can form only if interfaces are anisotropic. So if you want to see a dendrite, you have to include anisotropy. So I'm just going to talk to you for 10 minutes maximum about anisotropy. So first, in the sharp interface picture, we have done yesterday the Gibbs-Thompson effect, meaning we have studied the inclusion, a spherical inclusion of solid in the liquid, and we have obtained that the equilibrium temperature should be different from the melting point and should be proportional to 1 by R. Now this was under the assumption that the interface energy is isotropic. If your interface energy becomes anisotropic, that is, if the interface energy depends on the orientation of your surface with respect to the crystallographic axis, then there's a new effect, because now your surface can change its energy in two ways. Either it can change its surface area, that's the same as in the isotropic case, but it can also change its energy by rotating. Because since the energy depends on orientation, if the surface changes its orientation, it changes its energy. So if you change an energy when you rotate, this is not a force, this is a torque. So you can think that the anisotropy exerts like a torque on the interface. And now there is a very intuitive picture to understand the boundary condition that will appear. You see the surface energy, you can also interpret mechanically as a surface tension. So surface energy is like an energy per unit surface. You can also see that as a force per unit length. So if you cut the surface, and if you try to hold it, the surface tension will exert a force which is proportional to the length along which you cut. So in 2 dimensions, if I draw this, these are the orange arrows. If I have a little piece of surface, the surface tension pulls on both ends. And you can see if the interface is flat, then the forces are exactly opposite and you have no net effect. But if the interface is curved like here, you see if I sum up these two contributions, I will get a net force that goes from outside to inside. So this is called the capillary pressure or the Laplace pressure. And it's just proportional to gamma by r. That's the physical meaning of this quantity gamma by r that always appeared in our calculation. So if I have torques here, there is a new effect. And you can test it out next time you have a thin rod between your hands. If I have a torque, and if I apply a torque on both ends of an elastic rod, actually I will not have a net force acting on that thing because since it's a sort of solid, it will not do anything. But if I have a torque on one side that is stronger than on the other side, so you can try it out with your hands, then you will have a force acting on the whole thing that, depending on the difference, will go upward or downward. Okay? So meaning that a torque in itself will not induce a new force from the outside to the inside, but the difference between torques can. So there is a new contribution now, which is proportional to the difference of these two torques on the two ends of the interface. And so the capillary pressure now, instead of just being gamma by r, there is a new contribution, which is the derivative of the torque with respect to arc length. And this you can write as the second, you use the chain rule. So this is the second derivative times d theta by ds. Theta is the orientation, and d theta by 2s, ds is the curvature. Okay? So you get a new contribution that is proportional to the curvature and proportional to the second derivative of gamma. So the Gibbs-Thompson boundary condition now, instead of just being gamma by r, it's gamma plus gamma prime prime divided by r is equal to the thermodynamic part hasn't changed. Okay? So in 2 dimensions it's quite easy. You just have to replace gamma by r by gamma plus gamma double prime. Of course, now also, this is a capillary pressure. If you now look at the solid inclusion, since this function varies with orientation, the radius of curvature also must vary with orientation, so the inclusion is not longer spherical. And from this equation, you can get the equilibrium shape. This is called the Wolff construction. Maybe you have heard about it. This is the construction that allows you to determine the equilibrium shape of a crystal. I'm not going to talk more about that. Okay, just a small word. So yeah, here's the Wolff construction. Just a small word on 3 dimensions. Because in 3 dimensions, this all becomes quite horrible. Why is that? So you see now in 3 dimensions, the surface is 2-dimensional. So you can turn in 2 independent directions, right, left, or like this. So you have 2 components of the torque. And so you have to solve this Laplace pressure problem. And the rigorous solution is that you have to take the shape of your surface. You know, if you have a 2-dimensional surface, you can always define principal curvatures. That is, actually the curvature is related to the second derivatives of the surface with respect to, or rather no. I told you the curvature is d theta by ds. Now the orientation, you can derive it in 2 independent directions. So you get a vector, and if you take the variation of this vector, you get a matrix. So the curvature of a surface in 3 dimensions is actually a matrix. So you can calculate its eigenvalues and eigenvectors. So these are called the principal curvatures and the principal curvature directions. So all of this is math. It's differential geometry. And what you have to do is you have to find these principal directions and principal radii of curvature. And then you have to take the second derivative of your surface tension function with respect in these principal directions. And you have to multiply this with, okay. You see, it's quite horribly complicated. Okay, so, but unfortunately, that's physics. It's equilibrium thermodynamics of surfaces. Now, the good news for you is actually, if you do phase field, you never have to do that. Okay, why is that? Because precisely, that's why I have tried to construct phase field coming from thermodynamics. If you build in the right surface thermodynamics, then it should come out automatically. Okay? So how do I do that? Well, I have to go back to the surface energy. So I remind you surface energy, there is this double well potential and there is the gradient squared, and we have often had that there is these two coefficients k and h, k in front of the gradient and h in front of the double well, and we have often seen these two relations. Interface thickness is the square root of the ratio, and the surface tension is the square root of the product. So now, if I want to make the surface tension dependent on orientation, so I write this as gamma bar times an anisotropy function A of n. N is the unit normal vector. Well, how can I do that? Well, you know, see, I have an expression of gamma, and it depends on the coefficients of my phase field model. So I can invert this sort of. I can say, if I have a given gamma and a given interface thickness, well, I can calculate the coefficients k and h, which are just given by these formulas. Which means that now if I went to make my surface tension orientation dependent, well, I just have to make these coefficients a and kh orientation dependent. Okay? Now there is two methods, different methods that have both been used quite extensively. The first is, if you look at this, you say, okay, I put gamma of n. Well, I put the anisotropy function in each one of these coefficients, and I'm done. Historically, it was not done this way. Historically, people put actually the anisotropy only in the gradient coefficient, and then since you know that the surface tension is the square root of kh, then here you need to put the anisotropy function squared. So this is the way it was originally derived, and it was also used by Karma and Rappel. That's why also many people use this method. But the two are perfectly equivalent. Okay? So they give you the same energy. They give you a different variation of the interface width with orientation, but okay, that's a detail. But you should be careful, because if you plug this now in the free energy functional, so you have orientation dependent coefficients k and h. If you choose this method or the other method, you will not get the same equation of motion. Okay? Because remember that we had to take variational derivatives of this free energy. And if k depends on n, this brings you new variations. And why is that? I remind you, what was the formula for the variational derivative? So the variational derivative, I remember that was the derivative, the simple derivative of the potential term, plus this variation of the gradient terms, which I have explained to you on the second day. Now you see the unit normal vector, you can express like this as a function of the gradient of phi. Which means that if you put now in the free energy a function of n, then this part of the free energy of the variational derivative will also act on that function. So you will get derivatives of this function in your equation of motion that come from the proper variation of the gradient terms. Okay? Which means that if you do that, your equation of motion becomes more complicated. There will be new terms that are precisely the terms that are generated by this term of the variational derivative. So it's a bit nasty, but it's doable, especially if you are in 2 dimensions, and I think we will limit ourselves to this case, because in 2 dimensions, instead of working with the interface orientation, you can work with the angle between the normal and the crystallographic axis, and you see the angle you can simply express like this as a function of the two gradient components. So this is actually quite easy to derive. So you can find relatively simple expression for this part of the free energy, even in the anisotropic case. Okay? So, to conclude this part, if you have anisotropic interface energy, you have a new effect that comes from the torques that are exerted on the interface. You can incorporate anisotropy in the phase field model in a perfectly natural manner. And if you apply properly the variational derivative, you automatically get equations of motion. And people have shown by this matched asymptotic expansion technique that if you do that, you actually get exactly back this boundary condition automatically. That means the equation of motion for the phase field that you have to write down is maybe a little bit cumbersome, but it's far easier than to do the explicit anisotropic Gibbs-Thompson boundary condition in 3 dimensions. And this is maybe not always very much appreciated, but this fact is one of the major advantages of phase field models with respect to level set methods, for example, because here this physics is automatically incorporated, and you never need to evaluate things like curvatures, directional derivatives, or things which you would need to do in the level set method, where you have to program this Gibbs-Thompson boundary condition by hand. Okay? So with this, I'm at the end of this course. So we are just in time for having coffee, and if I'm not wrong, there will also be a group photo. Okay. And then after this break, Abik is going to take you and to do this in practice in the tutorial. So this morning is solidification, this afternoon will be anisotropy. Okay? And I will see you again in the afternoon. Oh, something else. I will, of course, also make anything that is interesting on the metallurgical scale. It will not work properly. Huh? What? Yeah, so this is a quite open question. Indeed, if you are interested in rapid solidification, then the solid trapping effect is there. So there is an interesting area of research that would be, so normally up to now we are usually choosing this constant of proportionality in the anti-trapping current such to eliminate solid trapping. If you are really in rapid solidification, then you should not eliminate it, you should just set it back to the natural value. So you have to find out what's the proper constant of proportionality that will probably be a function of velocity, and that will do that. So I have not seen any research done on this, but it's true if you want to apply this method to rapid solidification, that's what you should do. It's an open question. I'm pretty sure that it's possible. In the same way as to eliminate, you can just diminish it, the solid trapping effect.